Hey guys, this tutorial is for ORCA users and we will be looking at how to create custom basis sets. The featured molecule this time is a molecule that was voted Molecule of the Year on the CEN from the readers, and it comes from this paper called Hexasubstituted Benzenes with Ultrastrong Dipole Moments. I have a copy over here and we will be looking at this molecule named compound 3, which has a reported dipole moment of 15 dBi. So we'll see if we can get the same number or not. To begin, I have copied the coordinates from the SI of this molecule, and we can construct it in Avogadro, clicking in Build, Cartesian Editor, copy the coordinates, click on Apply, and when you close it, then you get the molecule as reported by the authors. So now you're ready to make your own input. So let's look at the basis sets offered by ORCA. If you go into the ORCA input library and click on basis set tab and scroll a bit from the top, you will get to this table that is divided into 4 rows, explaining the different families of basis sets that are hard-coded in ORCA. So first you have the most used one, the RIJ Def2 family. Then you have the same family but with minimally augmented diffuse coefficients that are used if you have an anion in your system, and then you have the CCPV Z, and then you have the augmented family of those. So the authors have used in their calculation B3-lip with this basis set, so we will be looking first at this last family, which that basis set is part of, and see what types of intricate concatenations of basis set we can get. So my initial input is this B3-lip, the smallest member of that family of basis sets. I optimize using the solvent model Cosmo in THF, and for me the calculation went very fast and converged with no problem. So using this, now what kind of variations can we have based on this easy case? So first, for example, let's take kind of a funky example. Let's say I want this nitrogen over here to be a special nitrogen, and I think that it deserves to have a larger basis set on this specific atom for some reason. So I can do this by first putting the default basis set in the general command line and then scrolling to the Cartesian coordinates, finding the atom that I'm interested in, and then putting this new GTO keyword and then the name of the basis set that will be applied to this atom only in quotation marks, followed by an end keyword. Here you'll notice that I have this print basis keyword. This asks the program to output the detailed information on the basis that have been used, and you want to make sure that the program understood correctly what is it that you wanted, so use it as soon as you type out more complicated cases than just one basis set for all. Another important thing is that if you do decide to use more than one basis set, make sure that you use the basis set from the same family and not crossover of some different types of, because it will probably lead to disastrous results, and we want to avoid that. Next case is if you want to use a bigger basis set on all atoms of the same type. So we're going to stick with nitrogens here, and again I put the default basis set in the general command line, and then I add this new section basis in which I put the new GTO keyword that will apply to all nitrogens this time, and the name of the basis set that I want to use for this atom type. Again, followed by an end in the line and an end to the section. Here I'm also using the MOREAD keyword, which allows the program to, instead of estimating the initial molecular orbitals, to read them from a file. The file in ORCA that contains the molecular orbitals has the GBW extension, and you need to put this keyword MO input, and then the name of the file in quotation marks if you want to use that. Alright, what else do we need? I think that's it for this one. Now, in the case of using a basis set that is not listed in this table over here, what can you do? Well, you can go to the EMSL Basis Set Exchange portal and create your own. So basically upload the coefficients that have been created by other people in the specific format, and the format that you need is Games US. So here you have a whole list of different programs. You should select Games US and then click on the atoms that you require. For me it's hydrogen, carbon, nitrogen, and on the left here you can scroll and choose whatever you want. When you're ready, you click on Get Basis Set, and then you obtain a list of coefficients per atom. Alright, so you will need to copy paste these coordinates into your input file, and it would look something like this. You get again the default basis set for all atoms, and then in the basis section you write the new GTO, the type of atom, and then the coordinates that you have copy pasted from the Exchange Basis Set portal. Here as well you will need two end keywords, one to end the new GTO section and one to end the basis section. It's important to have it. Okay, and now I want to talk about a little bit on the choice of basis set for your system, because I have recently had to do a whole long and painful validation of my basis set choice, and just want to give a very quick and oversimplified example as to what you can do. So in the paper that we started off looking at, we have the experimental value for this compound 3, and I wanted to see whether I can get to the same number as they got experimentally by using different size of basis sets with otherwise the same conditions for everything else. So I have picked to use this family, the first family over here, because I wanted to use this RIJ COSX approximation. So this very quickly, again, if you want to really know what this is, you should probably read more in detail the ORCA manual. This is a way to approximate and treat the integrals in your calculation a bit differently. It's basically shortcuts to your calculation, so it speeds up a lot the time required for your SCFs. So if you have big systems, it's particularly awesome because you save a lot of time. Now, if you want to use this approximation, you need to add another basis set keyword, which is this auxiliary basis set. So they're listed over here, and the input thus looks like this. So the smallest basis set that I can use is def2 SVP that requires an auxiliary basis set with the same name /J. And I have this RIJ COSX keyword to use this approximation. The medium size basis set is TZVP. Again, I have TZVP slash J, and then the big basis set is QZVP, and it's going to be the same idea once more. So now for the results. To get the value of the dipole moment as a magnitude, it comes as the more or less the last information in your output file, where it says ORCA property calculations. You can scroll a bit below that, and then you get this line, magnitude in dBi, and you get the value. So I have compiled my results for the 3 basis sets that I have used and the experimental from the paper. And what do we see? The small basis set is a bit off, but the middle and the big one are more or less the same thing. It's 0.3 difference, quite insignificant. However, if you look at the time it required for the calculation to go, you see that the medium basis set is by far faster than the QZVP. So this tells you that because the results are not significantly different and the time required is significantly different, you can justify your choice for the middle basis set as being appropriate based on this small study. If you are doing reaction mechanisms and you need to compare energies for your reactants and products, etc., it will be a bit more tricky than that. So I'll get back to another tutorial, but if you have molecular properties, it's a bit faster of a test. So I do realize that I haven't talked about the electron core potential, which is a very important thing if you are working with metals, for example. I invite you to read the ECP page over here on the ORCA input library and look through the manual. Also, I encourage you to read the general recommendations from the authors of ORCA. There's some good advice here as to what you should and should not do, which could be very useful for your calculations. And on this, I think I'm done, and I'll see you in the next video.